Well, welcome to the third lecture. Today I had planned to cover the perturbation to quantum corrections to the conductivity in weakly disordered metals. Both the hand-waving argument and also the Green's function calculation. But I got the sense in the last lecture that you guys also wanted to know about the details of variable range hopping. So what I did instead is I'm not going to go through the Green's function calculation till the end of the set of lectures, and I will give you the hand-waving way of understanding weak localization. And then I will move on to localization in 3 dimensions and talk about numerical methods for understanding the metal insulator transition in the Anderson model. And then after that, I'll take a step backwards and talk about variable range hopping in the insulating phase and talk about the paper by Ammegaukar, Halperin, and Langer, which I think is one of the nicest papers on disordered insulator that exists in the literature. So that's the plan for today. Let's see how far we get through it, and whatever I don't, we'll do in the 4th lecture. So the first point is that the correction to the due to Boltzmann conductivity due to quantum interference effects makes you don't have Boltzmann conductivity anymore, and therefore you don't have the result that the beta function is just d minus 2, which is what would happen in an homeopathy. And in general, the way to do this is there are 2 methods. There's many-body perturbation theory for disordered systems, which is one systematic way of trying to calculate the corrections. There's also methods using the nonlinear sigma model, pioneered by Wegner and his co-workers. And both of those are very highly technical subjects. So many people, especially experimentalists, were very they just had to take the answers at face, but it always is good if the theorists can explain why the results are what they are. And so that's what I'm going to actually try and do. So if you try and do the corrections in 2 dimensions, it leads to what's known as weak localization. That is, the resistance varies very weakly, logarithmically with either length or temperature. If you have a very good metal, that is, you start with a metal that has a high conductance, and then you look at the conductance either as a function of length, and experimentally that means looking at it as a function of temperature, and you find that the conductance keeps decreasing as you go to lower temperatures, but the decrease is logarithmic in temperature. So it's unless you're actually looking for it, you don't find it. That's the message. Okay. So I'm going to try and explain how this correction comes about. So normally, if you imagine a good conductor which has a bunch of impurities and electrons going ballistically and then gets scattered at one impurity, then it goes ballistic, then gets scattered at another impurity, and you keep on doing that, then the electron takes different paths from getting from point A to point B, scattering impurities anywhere in between, or even backwards for that matter, because you can have backscattering. And to get the total probability for an electron to go from some point A to a point B, you must sum the probability amplitude. That's what quantum mechanics says. It's because the electron is a wave, and you have to sum all the amplitudes, and then after you've summed up the amplitude, you square that to get the probability. So that's this formula right here, W, probability of getting from one point to another point B, is the sum of the amplitudes of all the different paths A sub. Amplitudes are AI. Now you can look at this summation, and you see that there are the diagonal terms, AI star AI, which can be written separately, and then there are the terms where I is not equal to J. And therefore, you have this sum over I not equal to J of A star I AJ. This is just algebra. And the first term is the sum of the probabilities of each path. And that's classical. That's the Rudolph-Boltzmann theory, basically. Okay. Usually the second term is just dropped out. And the argument that had been given, including in text by Bhatt, is that when you average over the different paths, the phase is varying all over the place, and when you sum over all these terms, they cancel out and you get nothing. And that is in general true, but there are a set of special paths where that cancellation does not happen. And that's depicted here in this slide. What happens is, if I'm trying to go from point A to point B, I can go straight, or I can go a curved path, or whatever it is. This is because of scattering of various impurities. Or I can even go through a path that looks like this. At a point C, it scatters back to the point C and then goes to B. These are what is known as self-retracing paths. And the point is that in this particular kind of a path where the path goes back to the same point, the particle could get scattered along this way, or it could get scattered the other way, clockwise or anti-clockwise along the contour. And along those two contours, you have exactly the same phase because you're going through the same set of scattering events. So that means those two paths are not just going to add incoherently, they are actually going to add in a coherent manner, okay? So in fact, what will happen is if I think of two different paths here in this case, A1 and A2, then this summation of all the four different combinations, including the off-diagonal combination, A1, A2 star, and A star 1, A2, they are all equal, and therefore you get 4 times the probability of one path. So classically you would have just got 2, now you get 4. Okay. So it's twice the sum of the individual probabilities. And the fact that this is enhanced probability at this point, return path C, means that there's a higher probability, okay, of being at C, and therefore a reduced probability for going to B, because the particle wants to stick around C, okay? And so it decreases the conductivity or increases the resistivity of the metal compared to the standard classical Rudolph-Boltzmann result. So I hope that is clear that these self-intersecting paths are the ones that are responsible for that. Now the question is, how do you estimate what is the effect of these paths? Because there are just oodles and oodles of paths that are there for the electron to go from A to B, and how do I estimate what's the effect of these kinds of paths? Okay. So the point is, you have to sort of think about the process of the electron path. The electron is going ballistically from one impurity to the other. Okay. So the natural quantum length scale in the problem is the de Broglie wavelength of your electron. And that is just given by this standard formula, lambda is equal to h over pf, which is 2 pi over kf. Okay. And so the question is, what's the likelihood of this return path? Well, you sort of have a situation where you have an electron which is sort of going in a path, and it's in a time t, it'll go as the Fermi velocity times dt. In a time dt, that's how much it'll go. And the cross section of this is going to be lambda, which is the de Broglie wavelength of the electron to the d minus 1 in d dimensions. So in 2 dimensions, it would be just lambda times df times dt. Okay, that will be the volume of this guy. Of course, in this time, in time t, if it's a diffusing electron, the electron is diffusing from one point to the other to the third, like that. Then in time t, it is covering a space which is dt to the d over 2. Okay, this is the square of the diffusion length. And it's basically going to a volume that is L to the d, where L is the diffusion length in time t. So to find out how much the conductivity is changed, you just look at the change in conductivity divided by conductivity is just going to be the ratio of the area that volume of this little tube that I've built integrated from time 0 to some time t relative to how much the electron will diffuse. So it's basically proportional to this integral. And I put in the minus sign because I know that the answer is going to be, should be negative. That is, the conductivity should decrease. Now, if you look at this formula and stare at it for a few minutes, you realize immediately that if the dimension was 2, d is equal to 2, then you have an integral dt over d, which is a log. So you're going to get the log of the diffusion length coming out. In higher dimensions, this thing falls off very quickly, so the corrections are small. Okay, so in 3D, you will have a smaller correction. But you can estimate what this is just by doing that integral. And what you find then is that in 2 dimensions, as I mentioned, you get a conductivity correction that's negative. The standard conductance result, E squared over h bar, and you get a log of, in this case, L phi over L. Now, L phi here is the inelastic scattering length or phase breaking length, again given by L phi squared is equal to d times tau phi or tau inelastic, because you're integrating from the mean free path, which is this small distance for scattering. This is the mean free path L, up to the point where the quantum interference effects will cease to exist. And we talked about the fact that once it has an inelastic scattering process, then all quantum mechanics is lost. You get back to classical physics. So as a result, what I hope to show you is I hope I've convinced you that you get a logarithmic dependence of the conductance on the length scale or on the temperature scale, as it turned out. Whereas in 3 dimensions, because conductivity is E squared over h times some length scale, this is actually going to be the length scale over which quantum effects stop taking place. And since L phi goes as some negative power of the temperature usually, because the inelastic scattering process is due to phonons or whatever else that you have in the system goes to 0 at 0 temperature, you find these corrections vanish at zero temperature. Here they don't, because it's log t, because it'll turn out L phi is proportional to t to some minus, to some power, and therefore the log will become the log with a different coefficient. That's about it. So these results that I've just shown you by hand waving arguments are exactly what you get if you do a full many-body perturbation theory. And if there's interest, I can, at the end of the lectures, when I come back from ICTS, I will be happy to spend a short time going over those calculations. Now I want to move on to experiment, because theoretical physics is not in vacuum. It has to deal with experiments, because experiments are reality. That's what I keep telling all my students. That is reality. Your theories are your imagination. Whether your imagination matches reality or not is up to you to prove. It's not up to the experimentalist to try and fit your theory. It's up to the theorist to fit the experiment, make their theory. So let me point out what are the experimental consequences of this very simple result that we got in the last slide. Okay. Since the inelastic scattering time varies inversely with the temperature, you normally it goes like some power law. It depends on what the microscopic mechanism is for the inelastic scattering. Many people thought it was phonons, and that certainly is possible. Another one people often put is electron-electron interactions. But whatever it is, it vanishes at zero temperature, so the inelastic scattering time goes to infinity at zero temperature in some power law fashion given by some exponent p. Okay. So tau inelastic goes as t to the minus p. And so if I put this back into in the formula before, since I had log of the L phi, which is square root of tau, I will get a logarithmic dependence with temperature. And that's a very clear prediction of the theory. Of course, until you know the mechanism for inelastic scattering, you don't know this number p. So, but it says it is of the order of e squared over h bar times some number p divided by 2 because of the log, because tau is, length is square root of tau. And so, but anyway, the log is very clear. So something you can check experimentally. And it turns out it was very soon verified in two-dimensional thin metallic films, as well as in two-dimensional semiconductor structures. And I will show you the data from that time. Okay. Then other thing that comes out, and that again will be part of the whole calculation, the range function calculation, is that when you put in a magnetic field in the system, the magnetic field puts in a natural length scale, which is the cyclotron radius. And that means it's this length scale, which is h bar c over EH, where h is the magnetic field, square root. And so this length goes to infinity at zero field, but at finite field, it is a finite length. And it turns out that it's a length which is quite reasonable in size at reasonable fields. And therefore, it cuts this interference effect once you reach that length. So instead of the effect being cut off by temperature, you can, by increasing the magnetic field, get the magnetic length smaller and smaller, and the quantum interference effect will go away earlier. If it goes away earlier, that means there's less negative conductivity, or the conductivity increases, or said another way, the magnetoresistance is going to be negative. The film becomes more conducting when you put a magnetic field. Now that's very rare. Usually when you put a magnetic field, it always increases the resistance. And so this was a very interesting result that had the opposite sign. So there is something that could be easily checked. Another thing that turned out that is quite important, but again, I will have to defer it to the perturbation theory calculation, is that if you have spin orbit scattering in a system, then the beta function, as we saw, the beta was d minus 2 minus some piece h bar 1 over g. Something like that. And it turns out that this one here goes to plus 1/2 instead of minus 1. And the reason it does that, it turns out, is because when you have spin orbit scattering, you have triplet and singlet channels, and the two of them add in the case of no spin orbit coupling, but they subtract in the case of the triplet channel changes sign, and it gives the opposite sign. And therefore, this not only changes its value, but it even changes its sign. So that would suggest that when you put in spin orbit scattering, the negative magnetoresistance will change into a positive magnetoresistance, because your localization effect has changed sign. Okay, so that's another thing that could be tested. And finally, one of the other possibility is that if you put magnetic impurities, again, you would get effect, because that would give spin scattering. So it turns out that in most cases, you've got qualitative agreement in the sense that the functional form of the effect was well described by theory. You needed a fudge parameter to fit the coefficient. That's about all that was needed. And so people just said, well, that's because we don't know all the details everywhere. But let's actually see what the data shows. So here's the first test of localization physics, which is experiment by Jerry Dolan and Doug Osheroff at Labs in 1979. And they plotted the resistance versus log of temperature, because they basically said that it should be logarithmic. And what you find is, yes, it is logarithmic, but in order to get this logarithmic dependence, which is shown here on the right panel, they had to actually go to the low bias region. Okay, because when they tried to actually determine the resistance at any given temperature, they found that when there was too much current through the sample, the resistance was current dependent. So you have to be very careful that each temperature you reduce the current or reduce the voltage across your sample until you get a constant answer. And it's this thing that you have to plot on the right side. You can't, if you plotted the data at high current, you won't get that same result. So this was one of the other lessons that was learned, that you really had to go to voltages which are, in this case, millivolts or less, in order to measure the resistance. And prior to this, many people, you're just measuring the resistance of a metal. It doesn't really, you should put a volt across it if you need to, but they had to go to sub-millivolt biases in order to get the resistance. And then as you go to lower and lower temperatures, you find that you may have to go to microvolts to get the answer, because nonlinearity is set in. So that is one lesson for the experimentalists. This is, Doug Osheroff is an extremely careful experimenter who got the Nobel Prize for finding superfluidity in helium-3. And but all his experiments, whichever ones he has done, are well known for the fact that they're very clean, very carefully done experiments. That's what gets you spectacular results. Now that was metallic films, but a year later, Dave Bishop, Dan Sui, and Bob Dines, also at Bell Labs, saw the same dependence in two-dimensional electron gases and MOSFETs. Okay, so here's another two-dimensional system. Its resistance should go logarithmic with temperature, and sure enough, that's what they found. And they also found that the Hall resistance goes logarithmic with temperature. I don't have time to go through that, but basically everything is supposed to be logarithmic because that's what weak localization gives you, is this correction which is logarithmic in 2 dimensions. Okay. So that also worked out very well. Of course, there's a little bit of issue about what is the actual slope and how that agrees with theory. Okay, and that I'll come to in a later lecture when I consider electron-electron interactions. It turns out that, if you just take the coefficient to be an adjustable parameter, you can fit it to localization theory. But then later on, theorists found out that electron-electron interactions also give logarithmic corrections to the Boltzmann conductivity with other coefficients. So then, of course, you have to add both those terms because that's what nature has. Nature doesn't choose to have electrons that don't interact. They do interact. The other thing I mentioned was negative magnetoresistance. Okay, so here is negative magnetoresistance in the 2-dimensional MOSFET. Okay, here's the resistance plotted as a function of magnetic field, and the data are these curves, and actually these data were fitted using the expressions that you can get out of localization theory. And the fit is pretty good. Again, the problem is the coefficient is not exactly what it said. Okay? But the idea that actually in this case the coefficient works better, it turns out, because what you can actually do is in the case of electron-electron interactions, it's the fact that the magnetic field couples to the electron spin that gives and there's a spin splitting of the bands that gives you the effect. Here, the reasoning for localization is completely different. It is that when the two-dimensional electron is going, and if you put a magnetic field perpendicular to your plane of the electron motion, then you have a natural magnetic length, an orbital effect, which is causing this negative magnetoresistance. So you can, by making sure that if you put the field in a parallel to the plane of the electrons and subtract that out from what is for the perpendicular to the plane of electrons, then you will get only the localization effect. And so you can isolate the localization terms from the interaction terms. And that's how actually, in the end, the whole resolution was made. Because once theorists said that there's also a log term coming from interactions, then of course the experimentalists said, how do we decide which one is the one responsible for the experimental data? And the answer there was that you can, by changing the direction of the magnetic field, one of them is affected, the other one's not. So that's how you can resolve between the localization effect and the interaction effect.
But if I put the magnetic field on the plane of the cushion,
yeah,
the cushion will not be confined to the plane.
No, if you put a magnetic field this way, yes, it will still, the spin splitting will still be there, right? The electron spin will still react to it. So the interaction effect will not change if you go from here to there. Whereas the localization effect really wants you to put a magnetic field perpendicular. And so you can distinguish between those two as a result of that. So what I'm trying to suggest is that, theorists have to be, clever in trying to figure out how to help their experimentalists. In this case, actually, the experimentalists were smart enough. They figured it out on their own. Theorists didn't have to say that. But, if the theorist just writes the formula and leaves it at that, it's not enough. That's what I'm trying to say.
One follow-up question.
Sure.
So if I have a perpendicular magnetic field, you said that you have the cyclotron radius, which is
right. Right.
If I put it in plane, there's also this process happening, but you're saying it's cut off by the thickness of your field, or?
Well, basically, that effect is the length scale. It's not, since the magnetic length is way bigger than the thickness of the film, it doesn't care about it. Yeah, it doesn't enter. That's the point. Then, of course, effect of impurities with strong spin orbit scattering. So one was looking at magnetoresistance of films that were that had no gold. These are magnesium films, and these are experiments by Gerd Bergman. He did a systematic study of a whole set of metallic films, different metals. And so this, in this case, is magnesium film. And what he found was that when there is only magnesium, you have negative magnetic resistance. That is this curve right here. Then he put a little bit of gold on it. Gold is a heavy element. Okay, heavy elements, there's a lot of spin orbit scattering because these are heavy elements, have electrons going at relativistic speeds, and that automatically couples spin and orbit. So what you find is that in fact you have positive magnetoresistance at small fields. And it's only when you go to higher fields that the negative magnetoresistance kicks in. And the more gold you put, the higher you have to go in field to see the negative magnetoresistance. So the fact that gold, the amount of gold determines what the curve looks like is a very, sort of a smoking gun for the fact that the negative magnetoresistance that's happening is due to no spin orbit scattering. That is a pure potential scattering problem. And when you put in spin orbit scattering, the beta function changes sign, and therefore the magnetoresistance changes sign. Okay, so
Question.
yes.
There was one plot where you had both the longitudinal conductance as well as the transverse conductance.
Yeah.
The whole one.
Right.
The argument why you gave us before that, why it should be log in two dimensions.
Right.
I can understand for longitudinal conductance.
Right.
The same argument, I don't see how I would push the same argument for transverse.
Well, the Hall effect has remained a bit of a mystery in these systems. Some systems show Hall effect, which is very similar to what the longitudinal resistance shows. And also in many cases, people have looked, this is all 2D with weak localization I'm talking about. But you can also ask yourself the question, I know that the longitudinal conductance goes to zero when the system goes from metallic phase to an insulating phase. What happens to the Hall rate? Does it or does it not go to zero? And the jury depends on whose experiment you believe. There are some experiments that show that it goes to zero, other that show that it's consistent with no change. So that's a little bit of a tricky issue, which has not been completely resolved.
This argument about this competing length scales that you have
Yeah,
on the board,
right.
that will not directly.
No, that's not. Yeah. Maybe the right way to say is that you see the log here, but you also see it in the Hall resistance.
Fine.
At this stage, that's the right statement to make. So that completes at least my brief overview of weak localization and the experiments that were done to look at weak localization. I'll revisit it again a little bit when I go to electron-electron interactions again. But there's a lot of experimental data that was collected, and there is a very nice review article by Patrick Lee and T.V. Ramakrishnan that describes many of these things. So I want to move on to a different way of looking at the metal insulator transition. You see, in 2D, you know that you only have an insulator, and weak localization, then it becomes strongly localized. So you really don't have a metal. That's the caveat is that, of course, if the beta function has a positive sign, okay, with strong spin-over coupling, beta versus log G actually goes that way at large G. And then, of course, we know that when there's a lot of disorder, it better go to an insulator, so it probably does that. Which means that there is a genuine metal insulator transition if you had only spin orbit scattering. Of course, there are no natural materials which have only spin orbit scattering. They have potential scattering as well. So the story is a lot more complicated. But one of the nice things is about numerics is that you can manufacture your sample. So you can actually study this problem. I'll briefly mention it at the end. So let me then take a step backward and say that in 3 dimensions, we actually have a genuine metal insulator transition because the beta function is doing this. It's starting from 1, d minus 2 is equal to 1, and it goes down and hits the axis somewhere for some critical conductance, and then below that conductance, we have insulator. Now this is, if you think about it, the Anderson model is a 1 electron model. So you can diagonalize the Hamiltonian, or you can do other tricks to understand what are the eigenstates of this, or what are the properties of the eigenstates, especially statistical properties of the eigenstates. So unlike many body systems, which I'll come to at the very end of my set of lectures, where the Hilbert space grows exponentially with system size, here it's only growing polynomially. In 2 dimensions, it goes as length squared. That's the number of eigenstates you have. In 3 dimensions, the length cubed. But it's still polynomial. It is not exponential. So there's much more of a role for numerical calculations to play in this case. And in fact, I would say that as far as the Anderson model is concerned, much more has been learned using numerical methods than almost any other thing. And I'll give you a brief summary of what's been done. So if you look at the phase diagram of the Anderson model, which I had shown a little bit some time ago, here is W over T, which is the disorder. T is the hopping, I remind you, between nearest neighbors, and we're going to put it equal to 1 basically by measuring everything in those terms. Here's the energy in units of T. And if there is no disorder for a 3-dimensional simple cubic lattice, the band extends from -60 to +60. It's a simple cubic lattice. Everybody knows what the dispersion looks like, the sum of cosines, and that's how you get the 6. Once you add disorder, you can show that there's an actual band edge given by this line right here and a symmetric line on the other side, which is just given by 6 plus W over 2T. That is the highest energy and the lowest energy state that can exist because of the sharp cutoff of the distribution. Remember, the Anderson model, P of W has a sharp cutoff at W. So there are many methods you can do. You can, for example, say that, all right, I'm just going to diagonalize the matrix for some disorder strength. So I'll get all the eigenstates from this end to the other end. And if I look at the localization length as I go across the transition on either side, I will get the exponent of the localization length, if there is an exponent. Turns out this is not a good way of doing things. And the reason for why this is not a good way is actually something that one of my graduate students, Sonika Jori, and I studied about 10 years ago. And what we found that rare fluctuation effects means that the localization length in this localized region is non-monotonic. And because of that, it's very difficult to, unless you have so much data that you can concentrate very close to the critical point, which is hard to do. Hard to get that much data. You don't have this is not a good method, practically. So instead, what is done actually is the most accurate method to date is something called the transfer matrix method. And what you do in this case is that it's derived itself from a one-dimensional problem where you look at the wave function at 2 sides and you integrate the Schrödinger equation to get the next side and then the next side and then the next side for any given energy. And the way you do that is using the transfer matrix. Now, if you're going to do 2 dimensions, then it turns out that you have to have some finite width of your sample, and then you start with the wave function on these 2 columns, and then you propagate. And in 3 dimensions, you imagine you have a cross section, you have to look at the wave function on this entire cross section, and the next one, and then you propagate that. Okay. But the method remains the same, which means that you're actually going to get wave functions of a very long bar in any dimensions whose cross section is L to the D. Some W to some number to the D, which I think many people use M as that number. So M to the D minus 1 cross section, and then you can go to as long a size as you want. And you use the property that when that size gets very, very long, the system is effectively one-dimensional. And we know that one-dimensional Anderson model, all states are localized, which means that they all have a finite localization length, including some rare fluctuations. They all have finite localization length. So what you do is you actually look at the localization length as a function of various parameters. Okay, so here I'm trying to explain the transform matrix approach. As I said, you sort of slice the sample up into L to the D minus or M to the D minus 1 sizes, cross sections, and then you keep on doing that for as long as you want. So M is the transverse dimension, and L is the longitudinal, the longer one dimension that you're integrating from. And what you do is you write the amplitude of the wave function on the ith and I plus 1th layer as a transform matrix times the amplitude on the I and I minus 1. So in one dimension it's very clear. These AIs are simple amplitudes. In higher dimensions, they are matrices, but that's a technical detail that one has to learn how to deal with. But basically what you do is you talk about these transform matrices, and then this transform matrix is just not at any given energy is nothing but a matrix that has the Hamiltonian, E minus the Hamiltonian, 0, and identity and minus identity of the off diagonals. Okay. And you see what this is telling you. If I want to go to much further down this thing, I just keep on multiplying transform matrices. I don't have to diagonalize anything. I just have to multiply. Multiplying matrices is much easier and much faster than diagonalizing. So what you do is you multiply these and imagine that the product of these two of the transform matrices is this M, which is up to some length scale n. And then you define gamma as the limit n tending to infinity of this matrix Mn multiplied by its complex conjugate to the 1 over 2nth power, okay, power. And this matrix gamma has eigenvalues which can be written in general as exponential of some number. These are called Lyapunov exponents. And it turns out that the minimum of these is what determines the localization length. It determines how slowly your wave function is going to decay. You know that it's one-dimensional, so you know that the wave function has to decay at long enough length scales. You can do 50,000, 500,000, million, it doesn't matter, it's just multiplying matrices after all. It's not so hard.
The localization rate is very large. Even though it is decreasing, the function decreases.
Right.
But the localization rate is very large.
Yeah, it can be large. Right. And so your length scale that you're going to is much larger than the localization length.
That's
Yeah,
right.
yeah, that's the point. You have to go to, yes.
So you have this size of maps that you take in the orthogonal direction.
Right, which capital M.
So you're assuming that your localization is less than that capital M or something.
No, actually it is of order M.
Because in the 3D, if I were to think of this as a lot of these patches
No,
being
so,
lined,
we are not going to claim that this one-dimensional system localization length is the right 3D. So let's think about 3 dimensions, okay? It's not that. You're going to use finite size scaling to actually infer that.
So you study whatever you get as this minimum gamma I
As a function of n, exactly. You find a localization length, psi I inverse, which is going to be a function of m.
Oh.
And in fact, you assume that it's a function of m over the correlation, over the real localization
You use
length
scaling theory on this one.
on this object, right, exactly. So I'm skipping over all the details, technical details. Those of you who want to know about the technical details, there are two sets of names that I would give. The original work was done by McKinnon and Kramer. They have a review article in the 90s of the earliest work. But the most reliable and most accurate work was done by two scientists in Japan, Keith Slevin and Tomiotsu. And okay. It's Ravin. These are the most recent results, and the previous work was Kiran Angus McKinnon and Bernhard Brown. Those are the two sets of names, right? And there are others who have done it also and have good results. But I think if you look at these are the original group of people who worked on this, and this is the people who pushed it to as much as is known today. There are other people who have done also. So the way it's done is that you look at this psi m at various values of disorder W using a long strip and cross-section M, and then you try to plot that psi M, which is dependent on M, that's the localization length you measured for that sample, divided by M. It must be a universal function of the actual infinite M correlation length divided by M for all W values. Okay, and so that just let me complete that. That helps you. You have to figure out what is this number, for which this versus 1 over that this quantity over M is universal. That the curves all match for different W's. Okay, and so doing that, you extract how the real three-dimensional localization length varies with the disordered parameter W. Because only by insisting that this is be a universal function of 1. Okay, and once you know how psi infinity of W varies, you see whether it is diverging at a given point with a power law singularity or not. And I'll show you the data, and that'll give you a little better idea of how this is done. Okay, maybe I don't know whether it's a few slides now, but it's never a bad thing to hear the thing and then see the data and hear it again. I'm happy to do that. So let me tell you what actually happened. It's also important to understand the sociology of the development of this. It's not, if I gave you the final answer and that was it, that doesn't give you any feeling for what actually went on. So in the beginning, when McKinnon and Kramer did this, they got an exponent nu which was 1.2 with an error bar of 0.3. Now, if you remember, in lowest order d minus 2 expanded, the answer was 1. It was 1 over d minus 2. Okay, so for d equals 3, the exponent should be 1. And they said, well, within our numerical error, it's consistent with one dimension. Okay. However, when they did more and more, and I got more accurate results, it moved up. And their final paper on the subject said it was 1.5 plus minus 0.1. So that's clearly not equal to 1. Okay. Now, Slevin and Otsuki started working at the turn of the century, okay, when the Japanese supercomputers came into being, and they didn't know they had so much time on those computers that, Keith Slevin and Tomi Otsuki took advantage of that situation, and they just ran with the problem. And larger sizes, more accurate analysis, and they obtained a value which in their latest paper is 1.58 plus or minus 0.02. So we're down now to the 2% level accuracy. I don't know whether I believe the 2% quite well, but it's certainly not worse than 5%, let's say. That would be, I would be very surprised if that number changed by 5%. Okay, clearly far away from 1. Okay. Okay. So it's interesting that this was the best method, but it involved doing the crossover from the d-dimensional system to the one-dimensional system. You had to do that analysis. That's what this is, this dependence on M. You're finally trying to let M go to infinity and to get the true exponent. Okay. And because things are easier in one dimension, everyone sort of feels that they should hang their hat to the one-dimensional problem. But nature's very clever. It makes it difficult, okay? So you have to really work hard with the one-dimensional crossover scaling in order to get the right result in higher dimension. And that's, I think, a lesson that anybody who's going to do numerics should be aware of. Because there was a completely different approach, which was taken by Macmillan. Macmillan, who's well known for the Macmillan TC equation and knowing. He also happened to be my PhD advisor. Very clever man. He did actually very small sizes: 4 cubed, 5 cubed, 6 cubed. That's it. He started looking at data from that using three-dimensional scaling. And of course, unfortunately, he died in a tragic accident very soon after this work. So much of this work was actually published after he died. There were manuscripts that other people got together, but he got an exponent which was 1.5 already in 1984, well before the strip method gave numbers of that kind. Nobody has followed it up, that kind of work. I don't know whether it is good or not, but it's something that that if you start in the dimension where you're trying to get the physics, you may not need to go to as large a size as if when you try to change dimensionality. That seems to be one, and I'll show you another situation where that is the case when I come to the quantum Hall problem. Okay. So these show very clearly that the lowest order epsilon expansion, or the expansion to order 1 over g, gives you a poor estimate of the exponent nu. It's supposed to be 1 over t minus 2. Okay. But then you can say, well, I'll go to higher order. Then that's what Wigner and his collaborators did. And the problem is that there were zeros for a few terms. Then when they got the first non-zero term and they converted it into the exponent nu went down rather than going up. So it's saying that this expansion is ill-behaved. It is first going away and then maybe it will converge. And that's a genetic property that one should realize. At least theorists should realize that when you're expanding around the upper critical dimension and going as 4 minus epsilon expansions do, then you're okay because you're starting with a system that has a phase transition and you're trying to see what are the corrections to it. Here, when you're expanding around the lower critical dimension, you're starting with a system that has no phase transition, and then it gets a phase transition. That's a much less well-defined expansion. And so, one of the assumptions always is that you can write it as a Taylor series expansion in epsilon, the difference from the critical dimension. Well, there is no reason to believe that there are not non-analytic terms starting from the lower critical dimension. For example, e to the -1 over epsilon. This you will never get with an epsilon expansion. One other place where that takes place is theory of superconductivity, as you know. It's e to the -1 over the coupling constant. Okay. So we have only considered potential scattering. And if one allows for spin flip scattering or spin orbit scattering, as I said, the beta function is modified. And as a result, we may expect quite generally that the localization length exponent will depend on what kind of scattering occurs, determines the transition from the metal to the insulator. Now, in real systems, potential scattering is probably the strongest. But, okay. Now, different cases, of course, can be done numerically. You can write a model that has only spin flip scattering or only spin orbit scattering, no potential scattering whatsoever. And then try and solve that model, just like you did the potential scattering model. And these correspond actually to the different symmetry classes that were in random matrix theory. We know that now There are not just 3, but actually 10 or 12 different universality classes depending on topology and all kinds of stuff. But in those days, it was hard enough for the theorists to even make the connection with random matrix theory. And all that was done by Wigner and Dyson, also Princeton people, one at the university, one at the institute, and that was done in the context of nuclear energy levels, of course. So when Otsuki and Slevin and their co-workers did the numerical calculation with great accuracy, you see, McKinnon and Kramer could only get 2-digit accuracy, and that was not enough to distinguish between the different cases. Here they got up to 3-digit accuracy, and when they got to 3-digit accuracy, they found that whether you have an orthogonal random matrix, which is the real symmetric Hamiltonian, just pure potential scattering, or unitary, where there's no time reversal symmetry as in a magnetic field, or symplectic with spin-orbit scattering, they got different exponents. So let me just show you a little bit of their data. So here is this plot of, now they call it capital lambda instead of psi over m, but it's basically the same quantity. And they plot it and they find that the data, so that for any given size, they will get only a portion of this curve. And then another size, they'll get another portion of the curve, and then a third portion. And they have to then decide on the proper prefactor in 1 over m to try and get these different curves, because nominally these curves will look like this. Then when you change your psi axes, then what it does is it shifts these. And so then they sort of patch onto each other. And that how well they patch onto each other is exactly what determines whether you've got a good exponent or you don't have a good exponent. That tells you the accuracy with which you can find the localization level. Yeah.
You mentioned that coefficient in front of these patches of data has to be toggled by hand.
Yeah, what has to be done is basically, if you remember, it was psi of m over m versus psi infinity over m. Yes. And psi infinity, of course, is a function of w.
Yes.
Okay, so then you have to figure out what psi infinity of w. If you fix psi infinity for some w, for another w, you will get a different answer, and then you see the variation. And as you change the psi infinity of w, these curves shift. And that's how you manage to get them to go together with each other. And as you can see, actually in here, there are 4 curves. Okay, there are 2 going up and 2 going down. Okay, so the reason why there are 4 curves is for each case, they have a metallic branch and an insulating branch, okay? And that's metallic, the insulating branch. And so you can't patch it up into one curve. The fact that you have to have 2 parts of the curve tells you that there is actually 2 phases. Okay? And the fact that there are 2 different sets of 2 pairs of curves is because one of them corresponds to the orthogonal case and the other one corresponds to the unitary case. And the exponents are different in the 2 cases, okay? The curves are different also. If you change the nature of the potential, the scattering, it changes the physics of the problem, okay? And here are, in this table here, are the results. They have sort of analyzed it more than one way, but basically what they say is the orthogonal is coming out to be 1.59 plus minus 0.03 or 1.60 plus minus 0.06. They've done subsequent, this is in their first paper, they've done more work, and the number I gave you at the end was a conglomeration of all the things that they have done. And then they did the unitary case, which is complex Hermitian matrices instead of when you're a magnetic field, and they get a result that's significantly different, but 1.43 with an error bar of 0.05 or so. Okay. Now, you needed to have this kind of accuracy to distinguish between 1.45 and 1.6. If the difference is not 3 times your error bar, or 4 times your error bars, and you cannot really claim that there's a difference. And that is the problem that McKinnon and Kramer faced. Okay.
But the exponential model for the engineering is that it's possible.
I don't think there's an easy way to look at that. It's just, these are numbers, they're universal numbers for different cases, and it doesn't, you can't, sometimes you can make hand-waving arguments, but in general, you don't have a good grip on what the exponents are going to be. Okay. I take a little bit of that back because it turns out that if you have unitary case, the correction is 1 over g squared. So then you might think that it's maybe you can make an argument based on that, saying that it's a smaller correction and therefore the exponent is coming out to be whatever it is. Okay. I can't do that in real time. If I have a better answer by Wednesday, I'll give. The other things I wanted to show you is that the conductance at the critical point is not one number like in the scaling theory that we did. It's actually a distribution of conductances. And this is a distribution plotted for the 2 cases. This one is for the dashed, this one is for orthogonal, and that one's for the unitary, I believe. And what you see is that there are these peaks at very low values, and so it's better actually to plot the distribution on a logarithmic scale. And you see how broad these distributions on logarithmic scale are. It's saying that there's a lot of fluctuations at the critical point. It's not and so you could also almost say, then why does a single, parameter scaling even work? Because the conductance is varying over such a large magnitude. There are ways to understand how that works, but nevertheless, it's important to realize that when we write down this G and beta of G, we are talking about some typical conductance and defined in a very precise way. I put down at the bottom the results for 3D symplectic case, okay, where you have spin orbit scattering. And there the error bars are significantly higher. They have only been able to get sort of less than 10% accurate, more than 10% error bars. So it's 15%. And it's a harder calculation because there are matrices involved in that symplectic case. I also mentioned that there should be a transition in 2 dimensions, and they have a paper studying that transition and the exponent corresponding to the transition in 2 dimensions with spin orbit scattering. So there's a lot of work there. I could, if I went through all their papers, I could give 4 lectures on that. But I think if you're interested, please go ahead and see that. They really do a nice job. Okay. So that concludes the second part of my my lecture for today. And I have it's 2:30 to 4, right? So I have about 25 minutes. Let's see how far I can get in with the Wegamper, Alprin, Langer paper. So now I've switched gears. I'm not talking about the transition. I'm not talking about the metallic phase. I'm talking about the insulating phase. And we had this very sort of interesting results from Bhatt saying that if you have localized states, you can have hopping conduction, and the way you get conductivity at a given temperature, the hop length changes. As you make the temperature smaller, the hop length goes bigger because it's a competition between the overlap and the Boltzmann thermal factor. So I will go through this paper, which does it from a completely different viewpoint. And it's a much more rigorous treatment, but again, it's important to realize that this is again for non-interacting electrons. Okay, so the assumption is that you have localized electronic states for some reason because of disordered potential, whatever have you, and the hops are being helped out thermally by phonons or some other bath, heat bath that is there. There are no electron-electron interactions in this calculation. So the first thing they said was, let's first prove that there is a localized phase. Okay. It's a typical Alperin approach to a problem. That is, first at least make sure that what you're starting with is actually valid. So the way they looked upon localization is they said, let's just consider two sites, okay, which have different energies. One of them has an energy E, and the other one has an energy E plus delta E. Okay, and I've just sort of schematically drawn some localized states around these two sites. They call them traps. Okay, and these traps are some geometrical distance r apart. And the whole calculation is in 3 dimensions, though you can do it in any dimension, but I'll go through the 3-dimensional calculation. So if you have a hopping, if you're talking about hopping of this electron, quantum mechanical tunneling to the other state, it's some prefactor which may have some slight dependence on R, but some polynomial dependence if at all. But the biggest thing is there's an exponential factor. The hopping is exponential. Quantum mechanical tunneling is exponential in distance. We know that from just solving a problem between two wells. Okay. Now, if you imagine that you have these two sites together and their energies, individual energies, if the other site was not there, were E and E plus delta E, and the hopping between them, because we brought them within some distance r of each other, is some T naught e to the minus alpha r, then the eigenstates, nature of the eigenstate changes dramatically whether this is larger or smaller than the difference delta E. If this is small compared to delta E, then the eigenstates are just going to remain mostly on 1 and on 2. If, on the other hand, it's much bigger than delta E, I can throw out delta E and I immediately see that the eigenstates are the bonding and the anti-bonding combination of the orbitals, 1 plus 2 or 1 minus 2. Okay, so if I take delta E equal to 0, then I know how to diagonalize this matrix. And I can diagonalize it for any delta E. Okay. So they said these two sites are connected if the energies are within the hopping T naught e to the minus alpha r, and those sites will get delocalized. Okay, so how do we connect sites? Okay, so if I have any site, okay, and I want to find out how many sites it's connected to, I take the density of sites per unit energy per unit volume. I integrate over all volume. I integrate over energy differences only that are between minus T naught e to the minus alpha r and plus T naught e to the minus alpha r, because only when the hopping is, the energy difference is smaller than the hopping, then they will not. Okay, if delta E is smaller than that, then they will be connected. If it is larger than that, they will not be connected because the eigenstates will remain on the site in question. And so you can do this integral because this turns out to have an exponential cutoff, and you get the answer that this is the number of sites that it will connect to any given site. And their argument is purely geometric. They said if this number is large compared to some number of order unity, they think it's about 2 or 3 or something like that. If you have a site and it's only likely to be connected to half another site, then chances are that this system is not going to have a connected path. On the other hand, if it's connected to a lot of them, then it will connect, and then you'll get a connected path through the system, and you'll get delocalization. Okay. So as a result, it says the condition for localization is that this number of sites that any site connects to has to be less than some critical number, which is pure number. They call it ETC. So what they've established is that if the density of states is very small per unit energy per unit volume, you will have localized states. That will be the systems. fate. You will not have a metal. So they've established that at low enough densities, there's not going to be a metal, there's going to be an insulator. And notice this is a completely different model. It's got sites that are at different places and things like that, as opposed to Anderson model, which has sites on a lattice and only the energies are random. So then the next question that they ask is, what is the hopping process when the sites at the Fermi level are localized? So you imagine you have some density of states that looks like this, and like in the Anderson model, in this model there will be some localized states at lower energies and extended states at these energies. Precisely how it varies is not important. What is important is that we are going to assume that the Fermi level, that the electron occupation is such that the Fermi level lies in the set of localized states. It does not lie in the extended regime. So we are in an insulator, a disordered insulator. Okay. So, and the other thing that is going to be assumed that the temperature is very small so that it's practically impossible for an electron at the Fermi level to get activated thermally to the extended state. Okay. That conductivity is just too small to be used. I mean, of course, it has to be self-consistently shown that the net conductivity is much larger than that, and that we will because we'll get Mott's law. So now what they do is let's think about the intrinsic transition rate of an electron that is on site I to an empty site J. This intrinsic transition rate will depend on the distance between the two electrons, two sites, and the energy difference between the two sites. Those are the two parameters that are there in the problem. Okay. So that tells me that if I want to think about what is the average transition rate from I to J, I must multiply this intrinsic transition rate by the probability that the site I is occupied, which is Ni, and multiplied by the probability that the site J is unoccupied. So let me also say that they are sort of taking a simplified view here. Spins don't play any role. Basically, either the site is occupied with an electron or it's not occupied. That's all there is. There are many sites, there are fewer electrons, and that's how they do the calculation. So the occupation number of the site I is either 0 or 1. And the other important thing is gamma ij is independent of Ni nj. That's the intrinsic rate. Here is the occupation number dependence, already explicitly written when you talk about the transition rate. So in thermal equilibrium, the average occupation of a site I is going to be given by the Fermi distribution. And so notice that they have just written e to the ei over kBt. Therefore, they are measuring all energies relative to the Fermi level. So they made the Fermi level equal to 0 energy, and every energy of all sites is measured relative to that. Okay. The other thing that they assume that the occupations are statistically independent, because these are independent electrons. We are not talking about electrons that interact with one another. Each electron. So the total conductivity is sum of what single particle conductivities. So that tells me that the time average Ni Nj is just time average Ni times time average Nj. There is no correlation between the occupation of one site and the occupation of another site. Now, we know that if there is no external perturbation like an electric field or a magnetic field or something like that, then the transition rate from some site I to some site J must be the same as the transition rate from J to I, because we have equilibrium. We don't have any current going in the system. So that tells me that capital gamma ij is gamma ji, and if you remember, capital gamma is given by this average over time. Then that tells me what is the relationship between the intrinsic transition rate, gamma ij, little gamma ij, and little gamma ji. They are related through this Boltzmann factor.
So this equation the relation gamma ij equals gamma A into in presence of electronic interaction.
No, in presence of electron interactions, even Ni and J occupations will be correlated. So, yeah, so we don't want to go there. This is a purely non-interacting model, but it's done very rigorously. Okay, so it's a good idea to at least have a rigorous theory of the non-interacting problem. Then I will go to electron-electron interactions, and at that stage I will rederive variable range hopping, but I will derive it like Mott. We don't have an equivalent to the Ambergaonkar-Halperin-Langer formula or derivation for electron-electron interacting electrons.
One question.
Yes.
So, saying that okay, electrons don't interact, so there's not correlation there.
Yeah.
But electrons have mutual statistics, right? So the usual minus factors and stuff.
Well, these are localized electrons, and we are thinking about not even spin. So there is no double occupation. There's nothing. So we don't really have. This is a very classical sort of very low concept.
So you're throwing away that correlation is very necessary. Or it's there in some sense because you're gaining or minus.
Yeah, you are taking advantage of, you are claiming that you want to have the site unoccupied, right? You're not allowing double occupancy. So in that sense, fermionic is there. But it could also be not occupied because of the energy considerations, right? You could have an on-site U and that will throw out double occupancy.
Yeah, but if I were to take a single determinant that try to do expectation I and j faithfully, will that be equal to expectation I expectation?
My feeling is that in the localized phase at very low densities, those effects will not be important. But I haven't actually thought of that. Now, the next thing that they do is, if you're going to do quantum mechanical tunneling, the dominant dependence of gamma ij, how the tunnel rate depends on the distance, is exponential at large distances. So there might be, pre-factors involving polynomials of Rij, but at large distances, this is the dominant dependence. And you notice it's got a 2 there because it's a rate, not an amplitude, not a tunneling amplitude. So if you consider low temperatures where the temperature is small compared to the typical separation between these two states, and further, this difference in energy is small compared to, say, phonon cutoffs like Debye temperature multiplied by Boltzmann constant, so Debye energy scale, so that you're not worried about the fact that there is no thermalizing bath. That's the main reason. Then what you can see is that you can write this formula. This formula satisfies every relation that we needed. We need the gamma ij's to have this relation in energies, and we need it to go exponential in the distance. So what you do is you say that when I'm going up the hill, that is, I go to a site with a higher energy, I have an exponentially small factor. But if I'm going downhill, I just go. The only important thing is I have to have an overlap. So that was a question that was raised some lectures ago, and here you can see specifically that has been taken care of, that it's only going uphill that you have the thermal factor, not going downhill. Okay. And Ambergaonkar, Halperin, and Langer call this the quantum limit of the hopping formula, because before that, there was a lot of classical hopping pictures due to people like Abrahams and others. In fact, it was Abrahams who first thought of the insulator, the resistance in an insulator in terms of a resistance network. And we'll see that there is a resistance network that comes out of this way of treating the problem. So in this previous formula, there's this prefactor gamma naught, and you can ask what does gamma naught depend on? And the answer is that it depends on the electron-phonon coupling strength in this model, because phonons are the Bhatt that they're talking about. It depends on phonon density of states, other material parameters, but it does not vary very strongly with energy of the system. All the energy and the distance dependence is already taken care of these factors. So you can then do some algebra and convert it into this capital gamma. And it turns out that capital gamma is equal to this rate gamma naught, which depends on materials parameters, the exponential factor, and then the energy factor has three: how far the initial state is from the Fermi level, how far the final state is from the Fermi level, and what's the difference between the energies. And you can see that their Fermi statistics is playing a part, right? I mean, it's saying that is the site occupied, is it not occupied? All that is coming, and that is what is giving rise to that. So there's no question that fermionic nature has been taken care of in this treatment. And this is in thermal equilibrium. Okay. Wondering whether I should go. Let's see, where is the next place that I can stop? Okay, let me go on for a few minutes. I may go on a little bit beyond 4 o'clock, but we started a few minutes late, so let's do that. Okay, I think, so the next thing to do is you set up all the problem. Now you have to calculate the conductivity of this and show that it looks like a resistance networking. So you ask yourself the question, that suppose I put in a small electric field E, what's it going to do? So now, of course, gamma ij will be dependent on this electric field. And the way it will depend is that the energy difference will be changed by the potential that the field times Rij. Okay. And so it'll go from the value at zero field plus some change. Similarly, the quantum occupation number will change because the local chemical potential will change when you put on a field. Okay. Again, they assume that there is no correlations in the current carrying state, just like there was none in the state without any current, without any electric field. Okay. So then you just have to sit down and calculate the net flow from site I to site j. Since it was zero when there was no field, all of it depends on these deltas. Basically, how did the gamma ij change? How did gamma ji change? How did occupation of I change? How did occupation of j change? And these factors are just standard. If you've ever done Boltzmann transport, you know that's how you calculate conductivity in a very simplistic model. Go look up Ashcroft and Mormon if you haven't. Okay. And you could, as a result, what it turns out is that it's given by 1 over kBt gamma ij naught. You use the formula that you have this is all at zero field, and you get, it's basically gamma ij naught over kBt times E times the electric field dotted with Rij and the chemical potential difference. Okay. Now, this is actually the potential difference, basically, between two sites. It's not E dot Rij. Okay, that's the crucial part that actually was missing in the original draft, I believe. Okay. Once you put that in, it says very clearly that the conductance, since this is the potential difference and this is the net flow from site I to j, the conductance is just going to be this number. Basically, it's obviously going to be proportional to the electric field or to the potential difference. So that's that term here, and the rest of it is conductance. And E squared over kb, there's an E squared factor that comes in because we're going into electrical conductance rather than number flow, and E squared over kbt times gamma ij naught. And gamma ij naught, of course, it depends on Rij, Ei, and Ej. And so this quantity can be interpreted as the conductance between sites I and j, just from this formula.
And this is also symmetric.
Hmm?
This is symmetric. Like if I interchange this is high and there.
Yeah, it is symmetric. Yeah, that's a conductance, right? Because we have a formula for this fellow, right? We have a formula for that guy right here.
Right.
Yeah. Okay. So now what you have is you've got a bunch of sites. Let me write this down. Randomly distributed. Some of them have electrons, some of them don't. And I have an effective Gij between any two sites. That's the conductance. Inverse of that is the resistance. So it's just a resistance network. And the question is, how do you calculate the resistance across this network? And one of the things that is very important to realize is that this is not a standard resistance network. You can't just, put it on a computer and get it done. It won't work that way. Why? Because these Gijs are exponentially dependent on various factors. So they vary over orders of magnitude. So it may be that this is 1 and this guy is 10 to the minus 17. Okay? And you have to find out what is the conductance of such a network. And you can't have an engineering approach to that, right? You'll say, well, let me just find out in a small region and then I will average or something like that. It doesn't work that way. In fact, what happens is that, I just wrote the conductance or resistance of the network, and then, so the overall electrical conductivity will be given by some characteristic conductance of this network. How we find the characteristic conductance is where the beauty of the calculation lies, divided by some characteristic length scale. Now, you can argue that this thing, G tilde, depends exponentially on all the distances and temperatures and everything, whereas this is only polynomial in the distance, so we're not going to worry about that. All the interesting behavior is coming from this average characteristic conductance. So what is this network going to look like? They say it consists of 3 parts, and once you think about it in that language, you realize it's absolutely the right way to look at it. There are those Gijs which are very, very large, and that's just shorts, basically. You can, you can just join those 2 points. This point, for example, these 2 could be put into 1 point, doesn't really matter. Okay. Then there are these very small conductances, and if you snip them off, nothing's going to happen. So to find the resistance of this network, you start snipping off the smallest resistances. In fact, if you have this to this, that's exponential of minus 100, that is not an interesting conductance. Just drop it. So you keep dropping it, but if you drop too many, then what will happen is you get an isolated patch here, an isolated patch here, an isolated patch here, and they won't connect up. So you have to stop at precisely the point where the system is still percolating, that they are still connected. You have a connected network, and you throw out all the low conductances or high resistances until the connectivity still remains. So basically, you're talking about a percolation problem. So that's what this argument goes through. And then you need to just calculate what that is, okay? So in order to calculate GC, you use the fact that you use the formula for gamma, and you get the result that this quantity has to be less than gamma naught over gamma C. Gamma C is the GC over whatever, KBT GC over E squared, okay? Now, if you look at this formula, you can immediately see that it can be written in the form that Rij cannot be larger than some amount, or this combination of energies cannot be larger than some amount, because the sum of them has to be less than 1. So this is just algebraically rewriting that formula there. So that tells you that the maximum length that these guys can have is some amount. The maximum energies that they can be far apart from the Fermi level is also some amount. And so the total number of sites which have E less than E max is just from minus Emax to plus Emax times the density of states. So that's the number of sites. And sites are separated by distance that have to be less than Rmax. So that tells me that this number of sites times Rmax cubed in 3 dimension, there must be is some dimensionless number. Because R has to be less than Rmax, and energy has to be less than a certain amount. And that gives me how many sites there are. And we must have the sites such that the density times the distance, typical distance between them cubed, must be some dimensionless number that is not too small. Okay, order 1. Now, if you analyze this formula in terms of the microscopic parameters, what you get is log of gamma naught over gamma c. It looks like that, and there is your 1/4. Okay, conductivity is exponential minus T naught over T to the 1/4, but T naught is given in terms of this, in this model, in terms of this critical nu c and alpha and density of states at the Fermi level. Okay, and there are power law prefactors. They say nothing about. They say that we can't tell you anything about that. All we can say is that that's the dominant term. And in what sense is this formula exact? The statement is that T over T naught to the 1/4 times log of sigma kt over E squared or gamma, E squared gamma naught alpha goes to -1 as T goes to 0. That's a strict mathematical statement that they can make. Of course, they don't know what nu c is, and so the parameter T naught is not known, anything like that. But they know that the functional form is correct. And I think I'll stop at that point. I've taken 5 more minutes, but I promised that I would go through this paper. And I think you may want to go through it yourself again to convince yourself of this argument. But I can say that this is one of the most beautifully written papers that I've encountered in 50 years of commencement. So at that point, I will stop. Any questions?
Mathematics of where you introduced this gamma c.
Yes.
What was the exact constraint on it? That gamma c has to be less than the rate or what?
Yeah, no, the point is that, yeah, so basically what it's saying is that you have to change your GC. I mean, that's the threshold, right? And you have to change it such that the percolation happens. So there has to be some average number of bonds per site. If you don't have that sites connected to others with a certain number of bonds, then they will not percolate.
I get the physical picture.
Right, right.
I don't know how it translates to the math.
Oh.
There are 3C. The first equation that
Right. So basically, that comes from two previous equations. One of the
is the expression of gamma. Gamma ij.
Right. Exactly.
How do you compare this to gamma c? Gamma naught ij is compared to gamma c.
Gamma c. Right. Well, basically, it's saying that gamma c is just related to GC through this formula. Okay, so that's what that is. So it's telling you what is the, first you find the critical conductance. Of course, that is a numerical procedure to find it, but it is some value, and therefore it of course enters all these parameters, Rmax and Emax.
Right.
But once you have it, these are finite. These are their dependence. Rmax is given exactly by that, and Emax is given exactly by that, multiplied by KT. So then you can put that into your formula. So the functional form of the conductance is preserved. But you cannot say much about the numerical numbers. That is not something they can say anything about. They don't claim to. Are there any questions from the remote sites? I don't seem to hear anything from there, so I think we're done for today, and then we'll reconvene on Wednesday to talk about something completely different with electron-electron interactions. Okay. Thank you.
Thank you, Ravin. Bye.
Bye.